If anyone here isn't in the SAILea Discord server yet, I just sent out a link to our server. And please make sure to join that because that's where we'll be sending out notifications for any course, any event that we do. So that's the best way to be up to date with SAILea.
Yeah, so we'll start by doing like a quick recap of the decision trees and finishing what we had left, which I believe was the implementation of the machine learning portion. And then we'll get into some data processing and go through a Colab notebook on an introduction to data processing, which Anisha will start talking about in a little bit. I'll share my screen. Okay, so last time we started going through a Colab notebook on implementing decision trees. So basically what we did was we went through some slides talking about just the very basics of machine learning, supervised, unsupervised learning, overfitting, underfitting, all of that stuff. And then we decided to go through a basic example where we worked with the Wisconsin breast cancer data set. And we talked about different aspects of decision tree, and we also worked on a Kahoot. So I'll just quickly recap like what was in the notebook up to where we were, and then we can work through the rest of it. So we just loaded the data and, sorry, my screen's frozen. And then we decided to start by doing some data visualization, which is actually something we'll get into more when we're talking about data processing and the preliminary stuff you do before you start developing a model. So we just experimented with different features and seeing if visually we could see anything about ranges and values for the features that would correspond to benign or malignant features. And while doing this, we also talked about how to split the data into a training and test set for machine learning. And we decided to use around 1/3 of our test set, or I mean 1/3 of our entire data for the test set. So before I get into any new material, I just wanted to ask if there were any questions or confusions regarding what we covered last time. You can private message Anisha or I, or just put it in the chat. Because last time we did unload quite a little bit about Gini index and just the internal structure of decision trees. Yeah, so before I proceeded, I just wanted to kind of explain a little bit about the structure of our data again, so we would all be on the same page. So, oh yeah, I could definitely do a brief summary. So I'll just open up the slides that we had from last time, and I can just go through a little bit of the content. Yeah, so last time we started by talking about, sorry, we talked a little bit about regression versus classification. So basically, regression is just to predict continuous values, while classification is to predict discrete values. So actually, in the example we're doing today, we'll be doing a regression example because last time we stuck mainly to classification with the breast cancer benign or malignant classification. And then we also talked a little bit about training data, validation data, and testing data, and how these are the three general splits into different sets that we have while doing implementing a model. And then we also went through a little bit about metrics that we use to evaluate the performance of our model. So a common one to use for classification is just accuracy, and it's exactly what you think it is, just the number of correct decisions over total decisions. Yeah, so today, because we're doing regression, we'll show you guys the mean squared error metric that is commonly used for regression purposes. We also talked about a very important way to evaluate the performance of your model using a confusion matrix. So confusion matrices basically allow you to have a nice chart of the predicted values versus actual values and really um, get a feel for the performance of a classification algorithm with the false positives, true positives, and false negatives, true negatives. We also talked about a very important machine learning concept of overfitting versus underfitting. Overfitting is when your model adapts too much just to the training data given, and because of this, it doesn't do very well or as well as expected on the test data. While underfitting is that generally your model isn't trained for long enough, or your model architecture isn't correct. Basically, your model isn't able to get a good sense of the actual data. We then talked about feature importance, and specifically we talked about permutation feature importance, which allows you to see the importance of a feature by seeing how much it contributes to the overall prediction. And the way you do this is you're just going to permute all the values in one column or one feature and see how it affects the prediction. The more it affects, the more important the feature. We then started talking about decision trees, which is when we also started to use a notebook to go through an example. So a decision tree can be used for both classification and regression. In this example, it was just for classification, but decision trees can also be used for regression purposes. Decision trees have an internal method to determining the condition at each node, which is called the Gini calculation. And basically what the Gini does is it just measures the impurity in a distribution. Yeah, so for example, if this is a node in your decision tree, you can see that the Gini values are specified. And basically the way that the Gini is calculated is based on the purity of the split. So for example, I believe I gave this example last time as well. If you have like a collection of marbles and you have like 5 red and like 25 blue, that would be somewhat of a pure split, not very pure because you still have some of both types, but it's mainly just of one color. So your model wants to maximize the purity, which can be done through this formula, 1 minus the sum of all the probabilities for each class squared. So how exactly do decision trees use a Gini index? So the decision tree will choose a split function based on some of the features in the data. And based on this split function, the probability will be calculated of going to the left node or going to the right node. Then you can compute the Gini index for the left node and for the right node, and the decision tree will try to pick the split function that minimizes this value, and this will maximize the purity. Yeah, so as Anisha put in chat, if you guys have any questions about Gini or anything like that, feel free to, you can either unmute or just put it in the chat. Yeah, so that was the quick recap of what we went through last time with regards to decision trees. We also did a Kahoot, which I think covered a lot of this material. So if you guys have any questions. Okay, so now we can just finish what we have left in the notebook. So if you look at the data here, some of the dimensions or the features are mean radius, texture, perimeter, smoothness, and all of this is basically just to kind of describe the tumor. And the final target column, which the model is trying to predict, is if the tumor is benign or malignant. And then after that, we went through some data visualization, as I previously talked about. I'm just going through this again to make sure that we're all on the same page. And if you have any questions, you can obviously interrupt. So we can visually see if there's any correlation between certain features and the target column. And this just allows us to get a first-hand feel of like how our data is, how it's distributed before we feed it into a machine learning model. So I believe last time we stopped right before we got into machine learning. So as we've now kind of gotten a feel for our data, we can implement a decision tree classifier and see how well it performs. So what we do is we create a decision tree classifier, And max depth is actually an optional parameter, but specifying it with a depth allows your model to not overfit or underfit. And with experimentation, we saw that 4 was like a reasonable value, and you guys can definitely go on and experiment with this if you'd like. Okay, so the next thing that you have to do is do clf.fit on your training set. And though this might just seem like one line, this is actually what encapsulates all of your model training, clf.fit. So basically what you're doing is you're fitting your model on the training set, or in other words, giving it some exposure to different samples before testing it on some different values. You can then call clf.predict and .predict, .fit, all of these are different methods of the decision tree classifier. So yPredictionTrain is what we store as our model's outputs on the training, and yPredTest is the values or model on the testing set. So we can now calculate the accuracy. So I was talking about how for classification, accuracy is a reasonable metric to use because it expresses the model performance. So you can just call metrics.accuracy score. Metrics is a package that we can use for this purpose, and you can get the accuracy train and accuracy test. And I just ran this right before sharing my screen, and you can see that the accuracy on training here was 99%. Our model fitted completely on the training set as expected, and then on the test set, the performance was around 90%, which is reasonable. And a lot of times on a case-by-case basis, you would want to see how can you improve the accuracy, and especially with more complicated models. When we get into deep learning and neural networks, you'll see that you might want to go back, modify the number of epochs you're training with, the structure of your model, the number of layers, and all of that. But just for the purposes of this example, we're going to treat this as fine and just move on. Yeah, and as Anisha said, yeah, most of machine learning is really just making sense of the data. Pre-processing is like a huge part of it, which a lot of people just tend to gloss over, but it accounts for a lot of how your model performs. For example, if you normalize your data, or if you don't normalize it, that's greatly going to affect the outputs of your model. So it's very important to really have clean processing, and it's a very crucial skill when it comes to machine learning and implementing these models. So now we can display a confusion matrix to get a further feel of how our model performs. So what our model has here is a true label and a predicted label. So basically we want this column here. I hope you guys can see my cursor, but benign is 54, malignant is 114. We want to maximize the numbers in the blue and the yellow square because those are the true values where our model predicts correctly. We want to minimize the places where the model predicted malignant and the actual value is benign and vice versa because that means our model is messing up. Yeah, so you can note that in this case, obviously classifying a malignant tumor as benign is much worse than the other way around, though they both mean that our model made a mistake. Yeah, so about this, there might be a way we can improve this by placing more importance on classifying malignant cases, because in a real-world application, that would be a lot worse, and even just one case where a malignant tumor was classified as benign would be a very, very bad thing for the model to output. So before I proceed with this, I just wanted to pause at the confusion matrix and give you guys a moment to like collect your thoughts and let me know if you have any questions. Yeah, and if you guys could react with like a thumbs up um, if you're like following along and everything makes sense, that would be helpful. Mm-hmm. Okay, great. So we'll move on. Mm-hmm. Okay, so is there a way we could place more importance on classifying malignant cases correctly? So there actually is another parameter to the decision tree classifier. You can pass in class weight, which represents how important each of these classes are. So class 0, which is our benign case, we're giving it a weight of 1, while we're giving malignant 1,000. So what that means is that classifying malignant cases has a lot more importance, and this will be reflected in our model performance. So then after that, we can just copy over the same code that we had above for just calling and testing our model. And when doing this, and we print out the accuracy of our model on the training and test set, we see that there is a much higher accuracy. And this is a great thing because it shows that when we place more importance on just classifying malignant cases correctly, the model does a lot better. So this is just one small addition that we made to our model, and it already improved the accuracy by around 5%. So in this way, there are a lot of small tweaks and changes you can make to a model to make it stronger. And as I was saying, in the case of a neural network, which is a lot more, which you kind of have a lot more, like you can change a lot of things with it. You can change layers, you can change a lot of different things. Playing around with this is a very important thing to do because it allows you to maximize the accuracy that you can get with your model. So once again, we can display a confusion matrix of this thing, and you can note that the numbers have actually increased. We have less in the benign malignant, malignant benign categories, 3 and 10, compared to the 55 and 120, meaning that our model performance improved. Oh yeah, I can definitely go over what a confusion matrix is again. So a confusion matrix, it just displays the model performance in terms of true and false positives and true and false negatives. So what that means is if our model predicted correctly, we would expect to see a lot of numbers along the diagonal that's running down this way. However, if our model predicted benign, in the case of malignant, that's not a good thing. And the number is put in here, and it represents the number of cases in which this occurred. So basically a confusion matrix, it has the predicted labels on one side and the true labels on one side and represents the model performance. Sometimes this can give you more insight than just looking at the accuracy values. So you can note now that 6 more of the malignant cases were classified correctly, which means that our model performance has improved. Now, what if we were to look at the actual nodes in our decision tree? And this goes back to that idea of Gini index and really getting a feel for how our model, how each of the split functions for our model works. So here we've plotted the actual decision tree structure, and you can see that basically the oranges correspond to cases of benign or where the model's predicting benign, while blue corresponds to malignant. We have the Gini indices here, the split function on the top, which is basically a condition on one of the features, the number of samples that reach this node, as well as the class, as I was explaining. So if you look at the top, it seems to be that the perimeter of the tumor is the most important feature. We see that worst perimeter less than or equal to 127.2 is the first condition that our model picked in order to distribute the data, which is a very interesting thing to notice. So we can take a closer look at the Gini values. So in the second layer, which is shown here, the Gini value for the blue box on the left is 0.052. And you might be wondering, how was that calculated? So from the formula I showed earlier, 1 minus the sum of all the probabilities squared of going to each of the classes. Because the split here is 6 to 19, that means you have 6 of one kind of tumor and 219 of the other kind of tumor. Because the class is malignant, we can infer that the 219 refers to malignant tumors. And that means the Gini value would be 1 minus 6 over 225 squared minus 219 over 225 squared. If we go back to the marble analogy, this can be thought of as a collection of 6 blue marbles and 219 red marbles, which is quite close to being a pure distribution. So now we can think about implementing our feature importance. So while looking at the splitting functions does give you an idea of which features are important, performing permutation feature importance will give you a clearer idea of this. So we already went over permutation feature importance, but if you have any questions about this or how it works, feel free to let us know. So We can start by implementing the feature importance by using the sklearn.inspection module. And what we do is we calculate the feature importance by permuting each column 100 times and seeing the accuracy of the result. So the top 3 most important features after doing permutation feature importance seem to be worst perimeter, worst concave points, and mean concave points. And the first one here should look familiar. This was what we saw at the top, at our first node, of being one of the most important values, and same with worst concave point. So now that we have worst perimeter as being the most important feature, we can perform a similar data visualization like we did earlier. So we can do the category plot as shown here, where we have the worst perimeter and the target column. And you can see that values that are around less than 125 seem to be correlated with malignant cases, while parameters greater than that correspond to class 0, which is benign. So you can see here that this is quite an important feature because it's very clear to see that there is a distinguishing line of where our data splits from being malignant to benign. And if you plot one of the other features, you can see this, but it's a lot looser. You don't have that clear split as you have around 125, which shows that the feature isn't as important. So just before we wrap up with decision trees, I wanted to go through a little bit more explanation about Gini index. So for binary classification, because we only have 2 classes, the Gini index would just be 1 minus p squared minus 1 minus p squared. And you can plot this below. So over here you see that we just have a parabola. So what that means is that our Gini value is minimized when we either have a probability of completely 1 or completely 0. And that is exactly what we mean because we want to have a pure split, and that is what minimizes the Gini index. So maybe looking at this graph will give you a little bit more intuition for how Gini index works and why specifically we want it to be minimized. So I see a question in the chat. How does the size of the data set influence the results of permutation feature importance? That's a really interesting question. I'm not entirely sure about that. We can get back to you, but I think generally permutation feature importance, it works when you don't have too many features because or too many samples because you want your model to be somewhat affected by the shuffling of the feature such that it causes a change to the accuracy and the features deemed important. Okay, so hopefully that made sense to everyone. So here we'll be stopping with our recap of decision trees and delving into the Gini index, and we'll segue over to talking about data preprocessing. Yep, so I'll be transitioning over to data preprocessing. So let me just share my screen. And also, the person named A, would you mind renaming yourself to your actual name? Okay, so let me just scroll to the top. So basically, we wanted to create a notebook about data preprocessing because we feel that it's sort of like glossed over a lot when it comes to machine learning. But it's just as important, in fact, more important, because learning how to call and run a model is pretty simple. But knowing how to make your data so that it's ready for that is what takes a lot of time and work. So we put together this collab called Intro to Data Processing, where we'll be walking through an example with the data set called the Melbourne Housing Snapshot, which we got from Kaggle. It has a bunch of features of houses in Melbourne, like the number of rooms, the price, they're listed here. And it also has the price of these houses. So essentially at the end, we'll be running a model on this to predict the price. Okay, so let's just get started. So here at the top, we are just importing the necessary imports, just as we did in the previous notebook, pandas, matplotlib, numpy, and seaboard. We're going to first load the dataset, which is the melvdata.csv. Let me just run it. Yeah, and we're gonna just see how the data set looks like. So we see by doing .head that we have a bunch of different features like the suburb, the address, rooms, and you can kind of immediately see that like some of these may not be as important as other features, and also the date is kind of written as 3/12/2016, which might be hard for the model to really make sense of it because it has the date, the month, and the year like all in one. So it's hard for it to sort of extrapolate a pattern from it. So that's something we can keep in mind as we move forward. It's always important to also know how big your data set is. So we see that it has 13,580 rows and 21 columns. So, excuse me. Um, it's always important to also know what your features are because that helps us sort of make sense of which features are important and which are just sort of arbitrary. So um, here I'm gonna just print the list of all the different columns, and below here are what the features actually are. So we have features rooms, which is number of rooms, price, method, which just has like a bunch of different strings that have like either property sold prior, and then we have type, seller G, which is just a real estate agent, the date, which is a date sold, distance, which is the distance from CBD. We have region name, which is like west, northwest, property count, and a couple more. So the first thing that you can kind of see is that like some of these variables are like really categorical, like methods, which has like different strings like S, SP, PI, PN. And it's like it's better to always convert them to numbers. So here what we did was we took the specific column and we first saw that there are none that are like empty. So they're all like some string that was provided above. And then here we performed categorical encoding to convert the method columns into numbers. So we replaced each of the different strings like S, SP to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And this part over here, which is in place equals to true, just makes it so that you're not redefining a new data set each time you do this. So it's just going to be modifying the same Melbourne DF data set. So let me just run that. And now if we were to run the shape, it's always a good check because we see that it's like the same size. Sorry, just excuse me for one. To answer Emmy's question, it's a great question. Yeah, categorical encoding is basically the same thing as one-hot encoding. You're just converting your categories into numerical values for your model to use. Yep, sorry I missed that question, but great question. Um, so now we've successfully converted our method column to numbers. But we do have this other feature, which is the type column, if you see above. Type just has like once again a bunch of like different things encoding for something else, which isn't quite good for our model to look at later. So we're gonna once again encode it to numbers 0, 1, 2, 3, 4, 5 for each of the different options. And once again, we're going to specify in places equal to true so that we're not redefining new data set each time. Run it again. And once again, we see the shape isn't changed because all we're doing is just changing the numbers. So now the third step is sort of like, which columns do you think are sort of unnecessary and not as important for a thing? So once again, this is just an example. So this is basically what we thought wasn't as relevant. So for example, like the real estate agent may not be as relevant to predicting like the price. The address, so we decided to keep the longitude and latitude, but the address in suburb is kind of like sort of based off that. So we decided to ignore that. And similarly, council area and region name. So here we're just doing df.drop of these columns because we're just removing the ones that we think are irrelevant. So now we see that we have 16 columns instead of 21 because we have removed 5 of them. Does anyone have any questions so far? Yeah, just to like kind of explain a little bit about why we dropped certain columns. So for example, dropping the address column, we found the address column to be unnecessary because if you look at the actual data, we have latitude and longitude, which basically means that the address is a little unnecessary because the model can anyway find any correlation between the price, which is what it's trying to predict, and the latitude and longitude if it has anything to do with location. Anisha, do you think you could just scroll back up to the data? To the head? Yeah. And similarly, we thought suburb wouldn't be that important because we just kind of saw the distribution. A lot of it was very similar, like there's Abbotsford for a lot of them, and also having the location is kind of the most important thing when it comes to predicting the price, and that would seem like a little bit of redundant information. Okay, so I'll take off from where we left off. I see that there's a question in the chat. Can you permutate before drop-in columns to determine which are relevant? That's once again a very good question. Typically, you do permutation feature importance sort of like after you have like developed the model to see what features are important. This is sort of prior to that where we're just trying to get a sense of the data. Does that sort of Yeah, so as Ananya said, you can do it, but at this stage, it's sort of just about looking at it and seeing what you think isn't as important, and address and suburb just seem kind of redundant given that we do have latitude and longitude. But that's a good question. Okay, so now that we have done categorical encoding for the two features that we wanted to do it for, and we've dropped the below features, we can now focus on what I mentioned at the very beginning, which is the date column, which has like 3/05/2016, for example, which isn't really good for a model because it has date, month, and year all at once, and it has to sort of find that pattern that, okay, if it's like different years spread apart mean that like the last thing is just gonna be one off, which isn't that, it's just you making your model do extra work. So here what we're doing is that we're splitting the day into 3 columns with date, month, and year. So the way we're doing this is that we're first isolating just the date, and we're doing date.split using the slash because you know that a slash is separating the day, the month, the day, and the year. So we're using list comprehension to just split it by slash, and then we're creating the day list, which just has all the numbers with the days, the month list, and the year list, and then we're creating 3 new columns called day, month, and year, and we're assigning them to these lists. And then we are dropping the date column, so now we're just left with these 3. And once again, we're specifying in place is equal to true because each time we're modifying the data set, we don't want to be changing and creating a new data set each time. So now if I were to print the head, we see that we have date, month, and year as columns, and the date column isn't there anymore. Okay, so we also can note, if we go up to the top, that we have a feature called rooms, and we also have a feature called bedroom 2. And this is kind of strange because rooms and bedroom 2 could mean the exact same thing. So naturally, we'd want to check if that is the case. So here we're going to print the number of columns where they're not the same, because if they're not the same, then that doesn't really make sense because the number of rooms and bedroom 2, whatever that's supposed to mean, should be the same. Once again, this was a choice that we made because if you have 2 sort of redundant features, that doesn't really make much sense. So we see that there are about 676 rows that this is the case. And here we're going to drop all the rows where they don't match. Once again, we're doing this because if you have like two sort of redundant features that basically mean the same thing, and actually if you see above when we printed the head, a lot of them did match. So we want to sort of get rid of the ones that don't match. So that's what we're doing here. And we're left with 12,904 features. So some of them were dropped. Now sort of comes the part that sort of needs the most work and a real problematic thing for a model to deal with, which is the NANs. So this is basically when there's missing data. And this can be a real issue because if there's a certain feature that doesn't have as much data, this can cause issues for the model to predict. And also the model can't really deal with strings like NANs. Like it needs some sort of number, but just replacing them with zeros isn't also a good idea. So we're gonna have to do something better. So if we were to just simply use the drop NA function, which just basically removes all the NANs, we see that we lose a significant amount of our data set. We only have 6,478, which is quite a drastic reduction from 12,904. So obviously we can't really do this. This is not a good idea because too less of data won't be the best thing for a model either. So what we're going to do over here is that for each column, we're going to see how much NANs there are so we can sort of get an idea of which columns have more and which columns have less. So here we see that rooms type price method up till bathroom have 0 NANs, but then you have car that has 62, building area which has a lot, 6,141, and year built that's 5,114. And this is way too much, and there isn't really much we can do with that. So the best thing that we could do is just remove these columns entirely, because at this point they're useless for a model to deal with. So here we're dropping the columns. Yeah, so I see Anish, you put a question in the chat about what types of issues nouns would cause in a model. So in some cases, when you don't have too many nouns present, replacing with zeros isn't that bad of a thing. It just means your model is kind of going to ignore those values or just treat them as empty in the calculation. But if you have a lot of nouns present, say more than like half of your data is with nouns, in those cases, replacing the noun values with the mean of the other values would allow you to still kind of keep the trend that you see in the rest of the data, so your model can still use that information in predicting. Yep. Is everyone following? Could you guys sort of react with a thumbs up again, just to make sure that, for me to make sure that you guys are sort of understanding what's happening? Great. Great. So I'll move on. So now that we've removed these columns entirely, we also note that for the car feature, though there isn't as many NENs, there's 62, we can just drop the rows that have these NENs because we don't want to just remove the feature entirely. It's too less of an amount to just remove the column. So what we're doing over here is that we're just removing the ones that have them. Okay, so now we're going to be going to the next biggest part before you dive into the model, which is data visualization. So data visualization is just as important as actually doing any of this stuff because it allows you to just sort of get an idea of the overall distribution of features. And it also gives an idea of like, are there outliers? Are there like really erratic sort of points? So here what we're doing is that we're creating a bunch of subplots where we have, for each one, we're just graphing the distribution of all the different features. So here we can see that we have all 15 of our features in like a 5x3 grid, and for each one of them, we're just sort of graphing the distribution. And we see that for some of these, they're very obvious outliers. So like for postcode, we have something like all the way over here. Sorry, that's zoomed in. And over here, we see that it's sort of all clustered at the end. And this is not, it's just sort of to get an idea of how our data looks like. Okay, so Anish asked, how did the removal of columns with many NaNs affect the dataset's dimensionality and the model's performance? So we decided to remove the columns that had like a lot of NaNs because they wouldn't be effective for the model to use. So yeah, exactly. I see some people respond in the chat, but really we just removed them because they weren't that effective, and the dimension of the rows didn't change that much at all because we just removed the specific rows that had NaNs for cars. Okay, so as I was saying, there are sort of some evident outliers just to notice here, and outliers play a big role because if you have something that sort of skews the data entirely, it's going to affect how well your model performs on this data set. So that kind of leads us to our next topic, which is outlier removal. So here what we're doing is that for each column in all our columns, we are going to store the average, the median, and the standard deviation using the np.mean, np.median, and np.std features. And then we're going to print using a format string, the column name, the average, the median, and the std. So this sort of gives us an idea of like how, like the general distribution of each column and feature in our data set. So I'm going to run this one right here. So now that we sort of see this, we kind of have a general idea of sort of like how the average, median, and the standard deviation look like. We see that a good way to sort of remove outliers is to sort of like take the median and create like a different like threshold for a threshold high and threshold low, sort of bounding our data to have like the low threshold being like the median plus some amount and the low threshold being the median minus some amount. So here we create a function where we have the column name and of course our data set, and we create a threshold high by taking the median of the column and adding 4 times the standard deviation, and our threshold low is going to be our median minus 4 times the standard deviation, and these numbers like 4 was sort of come like we thought of it just by like running it and seeing which one worked. We actually first had 3 times that amount, but then we saw that we were removing too much. Wait, yeah, as Ananya said, threshold values allow us to remove outliers and sort of helps us bound our data to the chunk that we need and the chunk that's sort of like extraneous or an outlier. So what we're doing over here is that we're saying num not in threshold is the sum of the ones that are above threshold high and the sum below. This is purely just because we were curious to see sort of how much is not in the threshold. And this allowed us to sort of experiment with values and see what value of that we're multiplying by the standard deviation would work best. And then what we're doing over here is that we're just getting the chunk of our data set where the values like less than threshold high. And then over here, we're taking that specific data set and we're removing the ones that are above. So in a sense, what we're doing here is that we're bounding our values to be in between this threshold. And we're returning our final data sets. So, and out here, we're just calling this function with each column and printing the shape of the data set each stage so we can sort of see. Okay, I think I need to run everything from the beginning because I think I ran a cell twice because we have more data, but one sec. Does anyone have any questions at this point? Yeah, so as you can see, it's actually 12,000. I ran a cell twice, so I ended up removing something twice. But okay, so we can see that for the rooms feature that we have num, not, and threshold is 13, and the shape reduces. And for each one, we can see how much is not in threshold. And as you can see, there isn't like any number that's too big. So we know as a fact that we're not like removing too much of our data set, and we're left with a decent amount for a model to make use with. And now it's always a good idea to sort of see how the distributions of our features look now that we've essentially removed the outliers. So here I'm essentially just running the same code that I had above for each feature and seeing how they look. And as you can see, the data is sort of not at like one corner of the graph. Like it's sort of just distributed in an equal manner. Obviously, some of them is sort of like they're still not perfect, but it's definitely much better than they were before. Like for example, if I were to scroll up, we see that rooms over here sort of spans from like 0 to 10, which is rather like unnecessary. But if you were to scroll down here, we have it's really fits. It's in the correct range from 1 to 5, which makes sense because a house typically has like 1 to about 5, 6 rooms. We also see that longitude also has like a nice distribution, and it's not like in the corner. There's no visible outliers that you can really see. So once again, I just want to sort of emphasize the importance of removing outliers because outliers skew our data set, and that's obviously not a good thing for our model. At this point, I'll be passing it over to Ananya to take it over from here, but please feel free to type in the chat, and thank you to everyone who has been participating in the chat. It's really helpful to us. Okay, so we can move on to doing, now that we've done our data visualization, to moving on and doing some data analysis. Anisha, could you scroll down a little bit? Sorry. Yeah, so over here, we just decided to do a scatter plot, kind of similar to what we were doing in the decision tree notebook, where we see the correlation between the target value price and one of the other features. So we do latitude and the price, and we don't really see much of a correlation here. At least it's not entirely random, but we can't really deduce much from here. So we can keep that in mind as we move on further and finally get to training our model. There is actually something that I would just like to say about this one particular graph. We see that it's kind of interesting because it sort of peaks at like a certain latitude, which is just interesting to note. It's like a certain chunk of like latitudes sort of have an increased amount of price, which is just interesting to see. So the next thing that we can do is we can create a correlation matrix. And this allows us to see the relationship between different features in regard to each other, not just in relation to the price or the target column. So this can give us a better feel for how different features are linked together and how one feature will affect another feature during model training. So here with the heat map, black means 100% correlation, and obviously the positive diagonal will be all black because it's just the feature with itself. But you see purples and dark shades of red, and that means that there's some correlation between the values. So if you look at this region here, you see that there's a high level of correlation or a higher level of correlation than in other parts of the heat map. So let me clear the annotation. Okay. So if you were to scroll down a little bit, we can see that, for example, rooms and bathroom are highly correlated. And obviously that would make sense because normally houses with more rooms tend to have more bathrooms. So yeah, so that might be a reason why we see that. This just allows us to get a better feel for the data. But you can see that other than that, there doesn't seem to be much of a correlation. We see some medium reds, which means that there is medium correlation, but not too much. So this gives us some sort of an idea. So now we can print out the correlation values for all the features with the target column. So we've been seeing the correlation from looking at these visuals, but what if we just want to see it in a numerical form or in like a way such that we rank everything? So here we're sorting the values by their correlation with the price feature, and you can see that rooms is the most correlated with the price, with around a 52% correlation. So this is really interesting to note, and it also does make sense if we think about it intuitively. You can also see that latitude is quite a bit lower with a coefficient of 24 with 0.24. And if you look back at that plot that we had, we did see that there wasn't much correlation, so that makes some sense. Okay, I see a question in the chat. So I know correlation can be both positive and negative. Okay. Yeah, so over here what we did is we actually printed out the absolute value of the correlation. And this is because actually having a negative correlation and positive correlation, for example, if I had -1 and 1, they both mean the same thing in terms of the relationship between the variables. So for example, if the correlation is 1, that means there's a positive correlation between the two values. But if it's -1, it means exactly the opposite. In all cases where one is high, the other one's low, like that. So both positive and negative correlation both hint at a relationship between the variables. So ranking the magnitudes of all of them will allow you to really see how important the features are for the model. But that's a great question. Yeah, and we also can see that like day, month, year, all of those aren't as important. We earlier did split those into 3 features. That's why they're listed as 3 separate values here. So now we can move on to normalization. So we can use the standard scalar from the SAILea.preprocessing module. So what you see here is we're just normalizing our data in the general way, zero mean unit variance. And normalizing is really important, especially when you're doing deep learning, because you really want your data to have a clean distribution, and that just generally enhances model performance. It's just something that you always end up doing for training your models. Yeah, so correlations tend to only capture linear relationships most of the time. There you can't really deduce anything about nonlinear relationships between variables. Yeah, so before we get into the rest of the stuff, we just want to pause, ask for any questions before we conclude today's class. We can continue the rest of this next meeting. We have quite a bit about how we trained our model, train test split, and all of that stuff, and finishing up the data preprocessing. So multi-collinearity can sometimes lead to overfitting the model because it makes it harder to interpret the relationships, especially when you have multiple independent variables that are correlated to each other. So yeah, that's a good question. Any other questions? It could be about anything we covered, the decision trees, the recap, anything.
Before we move on, I just want to briefly say that in the future, all our course material can be found in the SAILea course folder. And to be able to access that, you can just join SAILea at sailea.org. There's a short application. If you're part of a club, you can sign your club up, or if you're an individual member, like a lot of us are, just make sure to fill out that form. It takes maybe 5 to 10 minutes, and we'll get back to you and share.
Thank you all for actively participating in the chat and asking questions.
Yeah, for anyone that doesn't know, the meetings are bi-weekly, so the next one will take place in 2 more weeks. So that should be the December 2nd. And if there is any change that goes on, or if we decide to cancel a meeting for any reason, we'll make sure to let you guys know ahead of time and send you guys the link too. And if you guys found this meeting interesting, just share the link with any of your friends, your own club, or anyone you think that would be interested in this type of topics, and that'd be great. Yep, see you guys all next time. Have a good one.